Okay, welcome everybody to our afternoon session of the Trident Scholar presentations. It's great to see so many midshipmen here in attendance, faculty, staff, coaches. It's great to see you here. So we're going to start this afternoon session with Midshipman Zachary Peng from the 7th Company. Chemistry major. From Jacksonville, Florida. He's also a diver on the Navy men's swimming and diving team. He has a selected medical corps, and in the fall he'll be attending medical school at the Uniformed Services University of Health Sciences in Bethesda, kind of like military medical school. So go ahead, Zach.
Thank you, Professor Schroeder, for that very kind introduction. My name is Zach Peng, right? And today I'll be discussing the progress towards the development of a new synthetic methodology, which I've been researching this year. I've been advised by Professor MacArthur as well as Professor Lin. Modern human life has been heavily influenced by the field of chemistry, a science that has enabled advancements in fields as diverse as pharmaceuticals and materials to the benefit of both the warfighter as well as a civilian. A well-known example of chemistry's impact on the development of pharmaceuticals is the creation of aspirin. Aspirin was developed through the chemical modification of a natural ingredient found in the bark of the willow tree, known as salicin. Similarly, chemistry's impact on the development of materials can be observed through the production of the commercial rubber tire. Originally discovered by indigenous people of Mesoamerica, the sap of the para rubber tree had many primitive applications. In 1839, the application of vulcanization to natural rubber led to the manufacturing of pneumatic tires. Both the evolution of aspirin from the bark of the willow tree as well as the tire from the sap of the para rubber tree relied upon chemical modifications of substances found in nature. My project describes the development of new chemical modifications, also known as chemical synthesis, with potential applications for pharmaceuticals and materials. So here's a quick overview of synthesis. Elements are the basic building blocks of matter. Most of the elements are metals. The rest are nonmetals, such as carbon, nitrogen, and oxygen, and halogens, such as chlorine, bromine, and iodine. Many of these elements are fundamental for the chemistry of life, biochemistry, as well as organic chemistry. Elements can be combined through a type of bonding known as covalent bonding. In covalent bonding, 2 electrons are shared between 2 atoms. This is shown here by the 2 dots, as well as a line between the carbon and iodine atoms shown here. The process of combining elements through covalent bonding to create larger compounds is known as chemical synthesis. Chemical synthesis is very similar to the assembly of Legos. As many of you may be familiar, Legos come in all different shapes, sizes, and colors, and can be clicked together to create larger structures. The way in which they're assembled determines the structure of the target product. In this case, it is either a plane or a boat, 2 products with very different structures and therefore different functions. This is analogous to chemical synthesis in that smaller compounds, known as reactants, can undergo various changes in bonding to form intermediates, which are on the pathway to forming target products. The chemical structure of a product determines its function. A consistent, high-yielding reaction capable of forming a specific bond is known as a synthetic methodology. Synthetic methodologies make up the bond-forming toolbox that chemists can utilize to create specific compounds with real-world applications. The best tools are capable of forming bonds from a wide range of reactants. This is known as synthetic utility. Chemists can improve synthetic utility by understanding the sequence of individual bond-breaking and bond-forming steps, which is known as the mechanism. Some of the best tools in the toolbox or methodologies are capable of forming the desired product in both high yields without any undesired side product formation. To describe this and illustrate this, let's take a hypothetical reaction. You start with 4 blue blocks and 4 red blocks, right? These are your starting materials for the reaction. Your desired product is a blue over red block combination. And let's say each blue block combines with this respective red block to form 4 pairs of this desired product, right? That's 100% desired product yield. In contrast, let's say you have another hypothetical reaction with the same starting materials, blue and red blocks, and you have the same desired product, but this time you only get 1 combination, right? That's 25% product yield, significantly less than 100%. The remaining reaction mixture can contain unreactive starting material as well as undesired side product formation. This is represented by the uncombined blue and red blocks as well as the blue over blue and red over red blocks. Right, the purpose that I'm describing the significance of reaction yield as well as potentially side product formation is because these concepts will be discussed in depth later during the results. So now some relevant previous work for my project. One of the most important synthetic methodologies developed to date is the palladium catalyzed cross-coupling reaction, where 3 chemists were awarded the Nobel Prize in 2010. The cross-coupling reaction typically utilizes a starting material known as an aryl halide. As seen on the left, an aryl halide comprises of a ring with 6 carbon atoms, with a chlorine, bromine, or iodine atom attached to at least one of the carbon atoms. Chemists often simplify the structure as seen here on the right, where the carbon and hydrogen atoms aren't shown, but the bonds between the carbon atoms are retained. You'll see this hexagonal structure in many of the future slides coming up. Additionally, this abbreviation with the R and the line through the ring represent a group of atoms that do not undergo any changes through chemical modification. Aryl halides can undergo various changes in bonding to generate new covalent bonds to the aryl ring. This is represented here by the starburst chart of reactions with the aryl iodine intermediate in the middle and the arrows pointing at various potential products that can be made through cross-coupling reactions. However, not all aryl halides can undergo various cross-coupling reactions to develop the desired product in high yield. Aryl chlorides and aryl bromides are typically less reactive than aryl iodides, despite being more favorable due to commercial availability as well as cost. Our research group has successfully developed CTC synthetic methodologies for the carbon-hydrogen, carbon-carbon, as well as carbon-nitrogen bond-forming reactions already. My research is focused on building the carbon-oxygen bond-forming reaction, or CTC methodology. This slide shows several pharmaceutical and material compounds that contain aryl rings, which can be synthesized through cross-coupling reactions. Examples include Prozac, an antidepressant, letrozole, a cancer treatment pharmaceutical, as well as MK-1026, a blood cancer pharmaceutical, and polyether ether ketone, or PEEK for short, a versatile high-performance polymer. I'd like to point out that both MK-1026 and PEEK contain the specific bi-aryl ether product that I'm trying to synthesize with my research. And we'll talk more about it later. Cross-coupling reactions are typically mediated by a metal catalyst. Chemists, for example, have successfully used palladium to catalyze cross-coupling reactions of less reactive aryl halides, such as aryl chlorides and aryl bromides. However, the low natural abundance of palladium causes it to be over $948 per ounce. That's pretty expensive, if you ask me. To combat this, chemists have been interested in using copper. Copper is naturally high in abundance and therefore only costs 30 cents per ounce. This is a fraction of the price that palladium costs, but copper is typically less reactive with the aryl halides like aryl chlorides and aryl bromides. A catalytic reaction can be illustrated by the catalytic cycle such as the one shown here, where an active metal catalyst complex is at the top, the M represents the metal, and the Ln represents the organic compound bounded to the metal. A reactant enters the cycle and undergoes various changes in bonding, leaving the target product to exit the cycle and the catalyst behind to be used again. Although the metal catalyst can be recycled, it does have limited lifetimes. Now, for the non-chemists in the room, ligands play a vital role in stabilizing the metal used in the reaction. In a similar fashion of how a harness secures a pilot with multiple points of contact to the plane so that they may complete their mission safely, a ligand secures the copper metal used in our reactions at multiple points of contact so that it does not undergo any undesired side reactions. Our research group has pioneered a novel synthetic methodology known as concurrent tandem catalysis, or CTC for short, where two catalytic reactions are used at the same time concurrently within the same reaction vessel. In the first reaction, reaction A less reactive aryl chloride is converted into a much more reactive aryl iodide. This is done by breaking the carbon chloride bond in this catalytic reaction and replacing it with a more reactive carbon iodide bond. In turn, this aryl iodide intermediate is then used as the reactant in the second reaction, reaction B. In reaction B, the aryl iodide intermediate is coupled with a specific phenol specific cross-coupling partner to form the desired product. This is very similar as to what our previous LEGO analogy described, where we start with smaller compounds, form larger intermediates, and finally form our final desired product. A notable advantage of our synthetic methodology is the ability to leverage the more reactive aryl iodide, but start from a cheaper and less reactive aryl chloride. In future slides, the CTC mechanism will be shown in this more linear fashion, like shown here. There are three goals that directed my research. The first one was the development of a novel CTC synthetic methodology to form specific carbon-oxygen bonds. The second one was to study the mechanism of this reaction, or the individual bond breaking and bond forming steps. The third one was more of an aspirational goal, to apply the CTC methodology that we hopefully develop to the synthesis of target pharmaceuticals or materials. This year, I focused on the first goal, developing this synthetic methodology. Now, to describe the development of the CTC esterification methodology, I'm going to call back to the Lego analogy one more time. When you first get a new Lego, it's a brand new box, right? And you open it, you have your little blocks, and then you also know what you want to make. But you don't know how to exactly assemble each block so that you get the product without your instructions. In a very similar fashion, to the development of our CTC esterification reaction, we have our desired starting material, which could be some kind of aryl halide, the cross-coupling partner, as well as the desired product that we want to make. But we don't know what these ideal CTC conditions are. What are the optimal conditions that we can run this reaction under such that we can maximize yield without developing side product? To determine these conditions, we utilize a process known as reaction optimization. In reaction optimization, a single reaction condition is isolated and changed, and the effect of that is observed on the product yield. We focused on three reaction conditions: type and amount of ligand, the solvent, as well as reaction temperature in our investigations. These following slides are to demonstrate and illustrate or show you what experimental reaction looks like in the lab. This first piece of instrument is called a nitrogen glove box. In the nitrogen glove box, we're able to combine the desired starting materials as well as catalysts in a microwavable reaction tube in an environment free of water as well as oxygen. Once we've done this, we will move the tube to a microwave synthesizer, so a very similar microwave to the microwaves that you have at home, just a little better. And we're able to heat the reaction at a specific temperature and under specific pressure controls. This allows us to run our chemical reactions at a fraction of the price that it would take conventional heating, like 1 hour compared to 24 hours. This picture on the right shows an example reaction tube after it has been heated and the reaction has been stopped. We then move the reaction mixture into an instrument called a gas chromatograph mass spectrometer, or GCMS for short, so that we can separate, identify, and quantify the products present in the reaction mixture. Shown here is an example GCMS chromatogram. As you can see here from these peaks, we're able to identify our starting materials, the final product that we're trying to make, as well as any possible side product formation shown by this peak right here. So we use this reaction optimization procedure to run over 150 successful chemical reactions. That's a lot of reactions, just for the record. And we focused on optimizing the reaction conditions for reaction B first. This is because reaction B can be a driving force for reaction A and encourage the formation of the aryl iodide intermediate and ultimately the final bi-aryl ether product. For the chemists in the room, this is an example of Le Chatelier's principle. Right? So focusing on optimizing the reaction conditions for reaction B first, we utilized a series of previously published reaction conditions in literature to guide our experimental design, as well as the known CTC mechanism. This table summarizes the various reaction conditions that we found in literature, which produce successful product yields. As you can see, we investigated various ligands, solvents, as well as temperatures for reaction conditions. Additionally, most of these reference conditions were run under conventional heating, whereas our methodology is interested in using microwave heating. There is one reaction condition which did use microwave heating. But an example of how we converted and adapted this reference reaction to our purposes under microwave heating is the use of 1,1-bi-2-naphthol or binyl ligand in acetonitrile. The reference literature reaction is shown in the scheme at the top. Under its specific conditions, they were able to achieve a yield of 55%. The conditions are once again summarized in this table right here, whereas our results, I'd like to point out that we used 200 degrees for the microwave heating, but only for 1 hour compared to 28 hours, and we were able to produce a yield of 80% compared to their 55%. The purpose of this is to highlight the potential advantage that the microwave can provide for our development of the CTC methodology compared to conventional heating. A separate reaction that we investigated was the use of cyclohexane-diamine ligand in butyrylnitrile solvent. Once again, the literature reaction is shown here. The conditions are summarized in the table. This is our adapted results. We utilized, once again, 200 degrees under microwave heating for only 1 hour compared to 24 hours and was able to produce a yield of 76%, similarly high to the reference literature yield. We utilized the GCMS, the instrument that separates, identifies, and quantifies, to identify what could have happened to the other 24%. Right? Once again, this chromatogram, we're able to identify here are our starting materials, our desired product, as well as this undesired side product, represented by this peak with a mass charge ratio of 232. The ligand itself has the M to Z of 142, and when coupled with one of the starting materials, we were able to calculate that the arylated cyclohexane-diamine ligand had a mass charge ratio of 232 corresponding with this undesired product. To confirm our initial hypothesis that this was what was happening, we performed another reaction using DMEDA ligand in DMSO. Once again, similarly, we were able to identify this undesired side product, and we were able to do the calculation to see that the arylated DMEDA ligand had a mass to charge ratio of 178, matching and confirming our suspicion that these ligands are susceptible to this phenomenon called ligand arylation. All in all, this slide summarizes the various results that we observed when testing each of these reaction conditions. As you can see, the reaction conditions which use DMG-HCl ligand produced the highest yield of 98%, while the lowest one used DMEDA ligand, which produced only 46%. The most promising reaction conditions for reaction B are shown here in green. Now, having established promising conditions for reaction B, we then have to shift our focus to reaction A. Because as a reminder, in order for our overall CTC mechanism to work, both reaction B and reaction A have to be conducted under the same reaction conditions because they're in the same reaction vessel. This table summarizes our results for both reaction B, the ones that we just discussed with their respective conditions, as well as the reaction A results. As you can see, the conditions which produced high enough yields for reaction B did not produce high enough yields for reaction A. Out of all the combinations, we were able to identify one set of conditions which showed promise for both reaction B and reaction A. With this, we combined the two reactions to form our CTC investigation, where we used cyclohexane-diamine ligand and butyrylnitrile solvent at 200 degrees for 3 hours, and we were able to produce the best result so far to date with a percent yield of 55%. This is still a work in progress, but just to give you a frame of reference, this 55% yield is comparable to methodologies that have already been published with less or more reactive aryl bromide halides, and we're using aryl chlorides, which are less reactive. So this is a really promising result going forward for future research. So in conclusion, for reaction B, the esterification of aryl iodide, we obtained yields up to 98%. For reaction A, the halide exchange reaction, we obtained yields up to 56% for aryl chloride. And ligands that produce high yields for reaction B do not produce high yields for reaction A, especially for our aryl chloride substrate. And to date, the highest yielding CTC A and B reaction conditions are cyclohexane diamine ligand and potassium carbonate and butyrylnitrile with a 55% yield for aryl chloride as previously discussed. Future work for my project includes continual reaction optimization for aryl chloride CTC esterification reactions, beginning substrate scope investigations, and isolating the product through liquid-liquid extraction, as well as column chromatography procedures. We intend to investigate if the mechanism of the reaction is actually consistent with the established CTC reaction that we know of, and we intend to conduct computational studies to develop a further understanding of reaction A. And finally, we intend to apply the developed methodology to synthesize compounds and materials of interest, for example, pharmaceuticals. You may be wondering what these possible examples and applications could be. First one is a pharmaceutical example, as previously mentioned, the MK1026 blood cancer pharmaceutical, as well as the second one is a material application, the PEEK polymer, the versatile high performance polymer, which has a versatile or a very diverse potential use in the fields of automobile as well as aerospace engineering through the application of gears as well as bolts, as well as in the medical field and the biological field through the form of orthopedic implants. But the point of this is to show that without synthetic methodologies and the development of these reactions, true application will not be possible. And so potentially developing pharmaceuticals as well as materials will enable us to better protect the warfighter, develop economical pharmaceuticals, and potentially enable advanced new technologies. I'd like to acknowledge Mr. Matthew Schroeder, as well as Ms. Savannah Schumacher, part of the USNA Chemistry Department, as well as Dr. Maria Schroeder in the Trident Scholar Program, as well as the Office of Naval Research. And a special thank you to Professor MacArthur and Professor Lin for all their support and love throughout this long, long year. And also, thank you all for coming here, listening to my talk, and for all your support throughout my time at the Academy. I'd love to take any questions that you may have.
Yes, sir. Congratulations on the work and thanks for a wonderful talk. Can you speak to the compatibility of other functional groups? Like are there any limitations on what R can be on the ring?
Yes, sir. So, are you talking about the cross-coupling reaction?
Yes.
I wouldn't say there's exactly limitations in terms of the compatibility. The biggest thing, right, is just how efficient the reaction could be, so that using palladium catalyzed cross-coupling reactions are extremely applicable and are able to synthesize pretty much all of these new bonds. So the difficulty, right, with the research that I'm trying to conduct is using the copper and being able to develop the same sense of versatility and application. Yeah, Finn.
Can you briefly explain why you started with the second reaction and then worked backwards to the first?
Yeah, absolutely. So the reason that I started with the second reaction first is because the presence of reaction B can be a driving force for reaction A, right? So essentially, it can encourage, it helps the reaction go towards the right and towards the product formation, right? So because of this, if we have a high yielding reaction B, then in theory, we only need a little, some formation of this intermediate product so that it can pull all the reaction all the way to the right and produce the final products. So it would be beneficial to first investigate optimal high yielding reaction conditions for the second reaction, and then go to the first reaction. Professor Smith.
Yes, very nice. I was wondering with the copper, what form it was, and whether you had thought about maybe using nanoparticles or something increased.
Yes, ma'am. Yeah. So we don't know exactly so going into the reaction, it's copper 1 that we're using. but during the actual reaction, we're not exactly sure which species it turns into. So that is actually something that we're hoping to look into for future work. And we have not investigated the nanoparticles application yet. So. Yes, sir.
So for the microwave heater that you use, what variables are you able to control? Are you able to control obviously the time, but can you control the amount of power and the frequencies?
Yes, sir. Not frequencies, but pressure, temperature, and pressure. Pressure, temperature, and power, and time, but not like specific frequencies. Sir.
Thank you.
Yeah.
Nice.
Thank you. Yes, sir.
Why 200 degrees? I mean, 270, why not go to 300 or 400?
Right, so that's a really good question. Ideally, the lower the temperature for the synthetic methodology, the better, right? Because if everybody needs a microwave synthesizer to run these reactions, right, that would not be as an available form of synthetic methodologies. And 200 degrees specifically because the aryl chloride substrate which we're using, there have been previously established synthetic methodologies in which 200 degrees is the ideal temperature for the breaking of the carbon chloride bond and replacing it with the carbon iodide bond. So specifically, it's really important for the first reaction, reaction A, halide exchange, and not 300 or 400 because once you get up to those temperatures, it's difficult to control the potential decomposition of products, right? Like when you start with smaller substrates, it's not that big of a deal, but once you get, like you could produce 100% of your desired bioactive products, but then at 300, 400, like after the initial formation, it can start to decompose, which you don't want that to happen. So. Yes, sir.
Outstanding presentation.
Thank you.
And you mentioned the aspirational component, you tied it in real well. Can you talk about the origins of your aspirations for this project?
Like with those specific applications?
Well,
or?
when these ideas originated in your brain, was there any motivating factor that drove towards this project and some of those?
Yeah, absolutely. So Professor McCarthy and Professor Lin have spent years developing the other CTC methodologies that I mentioned with the different kinds of bond-forming reactions. And carbon-oxygen bond-forming like CTC methodologies have just been exceptionally difficult to develop because they are slower than the other ones. So in terms of as to what inspired me to join this project, my professors explained to me the potential applications of developing a carbon-oxygen bond-forming reaction, such as like pharmaceuticals as well as like these materials. And the reason why I chose these applications is specifically because highlighted in red, there are these bi-aryl ether products, which are like directly the products which you saw earlier from the synthetic methodologies that I'm trying to develop. So these are aspirational, I will like highlight, but it's just to give you a sense of like the scope of this project, right? Like chemical synthesis is such a wide field, and it's difficult to have these applications without starting from the beginning, developing these methodologies.
Thank you.
Yeah. Yes, sir.
Fantastic presentation, Zach. Quick question. Do you think that this can be used for other like applications in terms of, so you mentioned carbon oxygen, but like carbon or any other elements like that?
Yeah, absolutely. So, for example, carbon nitrogen is one of the methodologies that my professors had previously developed, like the CTC amidation reaction. And if you know Kevlar, I don't have a picture of the structure up, but Kevlar is a polymer, right, connected by carbon-nitrogen bonds. So in an ideal world, you could apply that CTC amidation methodology to synthesizing Kevlar and creating those carbon-nitrogen bonds without the use of like palladium. Dr. Kennedy.
Very nice presentation, Zach, like everybody else pointed out. Obviously, the method has advantages in yield and time of reaction, but is it limited in scale? I mean, how much material were you using in those reactions? And if you talked a lot about converting it into more industrial processes. Are there industrial-sized microwave reactors?
It's a really good question. Not that I'm aware of. The microwave synthesizer that I use is about this big, and it's a single cavity, and the reaction tubes that I use are about like this big in diameter. So I think that my research is really more of an investigation of the proof of concept, but I would love to see it be applied on a much larger scale and potentially develop these applications if possible. Yes, sir.
Exactly. Congratulations. It's a great presentation.
Thank you.
Great briefing skills, a little sad you're not going to be in naval aviation. But, my real question is, you mentioned the scope of this, right? And I think your work, when you laid out your goals, really focused on what are you doing to make sure that this carries forward and maybe gets towards the aspirational aspect of it?
Yeah, absolutely. I think the biggest thing is that I have a successor. There's going to be a second-class chemistry major taking over my investigation of the verification reaction. But I think the biggest things is I'm going to keep in touch with Professor McCarthy and Professor Lynn and make sure that they keep working towards the development of this application. So, but yeah, that's it.
Okay, so in the midterm, we have to get to 5, so let's take it through your one last
Midshipman Miller, and over the course of this past year, I've had the privilege of working with Dr. Crabb and Dr. Hua on improving machine learning deep sequential analysis through recurrent transformers, also known as retrans. So to begin, artificial intelligence is awesome. I don't know about the midshipmen in the room, but I use ChatGPT every day. It can help me with some, not on homework assignments, but it can help with simplifying complex issues like black holes, so that even though I'm not in that field, I can understand it at least a little bit. In the field of computer science, it can help me to write code a lot faster when I'm working on my side projects. Here, in seconds, it can write a Python script to generate the first 100 prime numbers. It can even do your basic arithmetic problems for you, except that it gets it wrong. Wonderful. And not only is this a ChatGPT problem, here's Google Gemini getting the same problem wrong. Here's Anthropic's Claude getting the same problem wrong. And it's not just multiplication either. These models can fail to solve some fairly simple problems. Here I ask it, give me the index of each S in scissors. It says 0, 3, 5, and 7. The answer is 0, 3, 4, and 7. A pretty simple problem here. How many words are in this sentence? It says 8, the answer is 7. Now, I'm no astrophysicist, but I think that this should be a little bit easier than explaining black holes. Furthermore, it's not just counting in mathematics. These large language models can struggle with creating an original joke, contributing to a large code base, or solving logic puzzles. Artificial intelligence, in general, struggles at deliberate thinking problems. Over the course of my presentation, I'm going to present you guys the machine learning background so that you can understand this problem and why it occurs. I'm going to present some existing solutions and their drawbacks. I'm going to show you our proposed solution, how we tried to solve this problem. I'm going to explain our methodology of what experiments we ran, show you those results, discuss them, give a conclusion, and some future work. So, all of these large language models that I've shown you so far are too large, too complicated to code by hand. When we have problems that are very hard and we can't write the rules to generate output from input, we rely on machine learning algorithms, where we provide an architecture with many input-output pairs, and it generates the rules itself. We can then use those rules to predict what an output would be for an input that we've never seen before. One of the most basic forms of machine learning, specifically in deep learning or neural networks, is the feed-forward neural network. It's a basic building block of deep learning that is influenced by the idea of the human brain, where there are multiple layers of interconnected neurons, each with different weights, impacting computation forward, going from an input to output. Now, feed-forward neural networks are excellent at analyzing one thing, but they don't have a memory, so they can't analyze a sequence. If I passed in the sentence, the quick brown fox jumped over the lazy dog, it could look at each word individually, but not in series. To remedy this, the recurrent neural network was invented, which has an internal memory, a state that is brought from the output backwards into the input as the model analyzes a sequence. Its execution can be shown through this computational graph, where we can analyze the sentence, the quick brown fox, because we output a memory, bring that memory into the next word that we bring in, so that now we have that context of what we've seen so far. And this continues forward throughout the sequence. The recurrent neural network's memory, however, is very volatile and unstable because it has to be fully recomputed at every single time step. To make this model more stable, to make it better at long-term dependencies, the long short-term memory network, or LSTM, utilizes a consistent memory which is operated on by gates rather than fully being recomputed every single time step. However, the LSTM can still struggle with very long-term dependencies or very complex environments because it still has a limited size memory, And so attention was invented. You may be used to this type of attention, but in machine learning, this is what attention means. The most similar analog to attention in the real world would be a Google search. So each input produces a query, a key, and a value. A query would be what I search, what I type into the search term, what I want to look up. Each website has a key, a headline, that is selected based on how similar it is to my query. Once that selection takes place, the most similar keys and queries, we grab the values from those corresponding web pages in order to properly pull attention, to pull memory from specific inputs based on how similar they are to what we're searching for. So in recurrent neural networks and long short-term memory networks, we were taking some form of our output and passing that forward. With attention, we are pulling from the input. Notice that since there is no taking from the output, I can generate the third output before I generate the second one if I want to. This allows all of the outputs to be generated at the same time, allowing us to use GPUs much more efficiently and get much higher parallelism, getting faster results. Multi-head attention is a very common mechanism used in the current state-of-the-art architecture, the transformer model. This is the architecture behind ChatGPT, Google Gemini, and Claude's Anthropic, and essentially every single major large language model. It incorporates alternating layers of multi-head attention with feed-forward neural networks. That was the first architecture I presented to you. Here's the computational graph for the transformer. You can again see that because of its attention, it does not grab its own output. Rather, it only uses the inputs that it has seen so far to calculate the next output. This gives the transformer a form of amnesia. It doesn't remember the computations that it's already done. We think that this is the reason that transformers struggle with deep thinking problems. It doesn't have the ability to create an internal chain of thought that builds up over time so it can solve those deeper, harder issues. There are several existing solutions which attempt to remedy this area. First, verifiers, where a researcher trains a separate model to verify when the answer is correct and to guide the model and choose more correct answers. Second, thinking models is where a transformer is trained to initially output a chain of thought, guiding its future result when giving the answer. Exterior tools can be used, such as giving ChatGPT the opportunity to run its own Python code so that it doesn't actually need to solve the problem for itself, but rather rely on an outside function call. And finally, multi-shot, where a researcher provides the architecture with several correct examples before asking it to provide an answer. However, all of these existing solutions only improve accuracy to a point. They don't solve the issue. There are workarounds that do not address the underlying limitations of the transformer architecture. And they require significant additional computational power on top of the base model. This is where my Trident comes in, the recurrent transformer. Over the course of this year, I have worked on refining an architecture which reintroduces recurrence into the transformer architecture, bringing information back from the output into the input. This allows the model to natively build up interior chains of thought and solve harder problems more naturally. Looking at the computational graph, rather than pulling our input from the input for the multi-head attention, we're grabbing it from our previous output. We're also replacing the feed-forward neural network with LSTMs, mentioned earlier, so that it has an interior cached memory. This gets rid of that transformer's amnesia. It allows it to pay attention to its previous output, remember the computations that it has already done. A guiding principle of our research was computational depth, which is the number of operations, or in these graphs I've been showing, the arrows, between a given input and output pair. In general, an increased depth means that the model is more capable of deeper thinking, but that it may forget things, leading to difficulty in training. A shallower depth means that a model is not as versatile when it comes to deeper thinking, but it may have more reliable training due to immediate memory access. So, showing an example, this is our LSTM from earlier. It only has one path that a computational information can take from a specific input to output. And the length of that path increases linearly with the distance between the input and output in the sequence. In contrast, the transformer has two possible paths, each with constant length regardless of the distance between the input and output pair. This makes the transformer much better at memory recall, but worse at deeper thinking. Now, finally, our recurrent transformer, our RETRAN, has many different paths with a varying range of computational depth, from a constant length to a length that varies linearly with the distance between the input and output pair. This allows the RETRAN to use shallow thinking when that's more advantageous, for memory's sake, and it allows it to use deeper thinking to solve harder problems when necessary. Just to show a couple examples of that range of computational depth, just like the transformer, the RETRAN can have a constant computational length by passing the information directly from the input token to the output in the sequence using the multi-head attention, so that regardless of how many elements are in the sequence, it's the same length for computational length. But also like the LSTM, the RETRAN can pass that information forward through the LSTM's memory using a linear computational length. And not only this, the RETRAN can use any combination of these LSTM's memory and the multi-head attentions to achieve any range of computational depth between that constant and linear. So we tested our RETRAN against the LSTM and transformer on two specific data sets randomly generated to test the model's deep thinking ability. We tested varying model sizes to determine the scaling properties of the model or how making the model larger impacts testing performance. Our first data set that we used is integer arithmetic, utilizing problems between 8 and 30 characters in length. These consist of addition, subtraction, multiplication, and parentheses. We used 2.6 million training problems, 600,000 problems that the model wasn't directly trained on, but to validate its success, and finally 200,000 testing problems that were given to the model at the end of training to calculate the testing accuracy. A couple examples of the problems are shown on the right here. We also evaluated the RETRAN on a 3 Boolean satisfiability data set, where the model solves what one set of variable values makes a specifically formatted logical expression evaluate to true. These expressions consist of variable names, not, and, or, and parentheses. There were roughly 250,000 randomly generated training problems, 50,000 validation problems, 20,000 testing problems. This data set is significantly smaller because of the amount of time it takes to randomly generate these problems. Now, a simplified example of 2 Boolean satisfiability is shown here for your context. So the model would have to determine what value of x0 and x1 makes this equation evaluate as true. And there's only one solution for this, where x0 is true and x1 is false. And this is what a real example from the data set looks like. Significantly more complicated and less intuitive. So for our training, we optimized the training environment for each model in order to compare the models at their peak performance. For our testing, we monitored several values throughout training. First, the testing accuracy, which was the proportion of the testing data solved correctly with one shot at the end of training. Next, validation loss, which is a metric measuring the average distance between the model's outputted answer and the actual correct answer. And finally, the number of parameters in each model, which is the size of the model. It roughly correlates to how much energy and memory is consumed when the model is being trained. So, here are the models that we tested, a small, medium, and large of the LSTM, transformer, and RETRAN, varying in size from roughly 30,000 parameters to 1 million. And finally, our results. So, on our integer arithmetic data set, our recurrent transformer significantly outperformed both the LSTM and transformer at all sizes. I want to bring y'all's attention to the GPT-4o dotted line here. This is if you ask ChatGPT, the baseline model, to solve the testing problems through the API, we got roughly 58% accuracy. For context, GPT-4o is 200,000 times larger than our largest RETRAN, and our RETRAN scored about 22% better on the testing data set. It's a little bit unfair to compare these, considering GPT-4o was trained on all of English, and it can answer questions about the universe, where our RETRAN can only answer with positive and negative numbers. But it's still it provides context for how well our model performs compared to real-world state-of-the-art applications. Next, our final validation losses over the parameter count for each architecture. Again, our RETRAN significantly outperforms the LSTM and transformer at all sizes. It performs roughly as well as a transformer that has 10 times as many parameters. And you can see that this is validation loss, a lower number is better. The RETRAN has a steeper negative slope, slightly than the LSTM and the transformer, indicating that as the model sizes increase, this distance between the RETRAN and transformer is going to gradually increase as well. Next, we wanted to break out our testing data based on how long each problem is to see how well these models perform on easier versus harder problems. Again, my RETRAN beats the LSTM and transformer at every single size. We also tested it on problems that were longer than the problems that the models were trained on. So the models were trained on problems between 8 and 30 characters. We also tested it on 31 through 40. And just to test the generalizability, and the recurrent transformer, again, outperforms both other architecture types. Next, Boolean satisfiability. So over the course of training, the RETRAN, again, surpasses both other architectures significantly. Our large RETRAN actually scores 99.9% accuracy on the testing data set. I would like to draw y'all's attention to the LSTM falling off. This is how I mentioned earlier that when computational depth can get too long, the model can actually fail to remember things. That is what happens with the LSTM here. It begins to diverge because that computational depth is simply too great. Next, our final validation losses for the 3 Boolean satisfiability tells a very similar story to our testing accuracy. Lower number is better, and our RETRAN beats all. So in conclusion, we developed a new machine learning architecture, the recurrent transformer, which reintroduces recurrence into the transformer architecture, passing information from its output back into its input. This allows for much more efficient usage of parameters, reducing the model's energy and memory footprint. However, it does reduce an increased training time, roughly 3 to 5 times longer over our data sets. This results in a speed versus size trade-off, where the RETRAN is more appropriate with small data sets requiring deeper thinking, and when it's run on smaller devices. However, it may be less appropriate with larger data sets containing longer samples, where it might take significantly longer to evaluate. For our future work, we plan on implementing variable length computation, where the computer decides for itself how long to think. Recent research has shown that variable computation helps with these types of problems, such as solving arithmetic. We plan on implementing a chess-playing approach where we utilize AlphaZero's Monte Carlo tree search to determine how long to think for. Finally, we plan on implementing RETRAN on a natural language processing data set where we use English rather than arithmetic. This will test if those benefits translate to an English data set. It will require significantly more computational power and time to train, but it will allow us to determine if Retrian can scale to a large language model. Thank you all for listening. Thank you specifically to Professor Schroeder for helping to run the Trident program. Thank you to my advisors for guiding me along the way, and to the Trident committee for giving me this opportunity. Any questions? Yes.
I guess I'm wondering, it seems like once your AI model is out there taking output from various places, that your sort of training set or whatever could be corrupted, because isn't it, if you feed it a bunch of garbage, for example, right? And then how would it know that now it's getting bad data and bad results, and how much of a chance is there of that happening?
So that's a great question, and that's what some large AI labs are doing now. I think there's Google Gemini and ChatGPT are somewhat trained on Reddit, and so you will see people giving sarcastic answers, and the model believes it's true and tells people to eat rocks. That's an inherent issue when you get data from outside, and to combat that, you can clean your data better. You can verify what sources it's coming from. For instance, you could train your model solely on Wikipedia articles. Now, there may be some false information there, but it'll be at a much lower rate than if you use data from the internet in general. That's an ongoing issue, and it can introduce a lot of problems and security issues. Yes, Matt?
Can you go back to the final validation or the graph works?
Yep.
So are we supposed to see some sort of linear relationship or logarithmic, or I see that's 3 axes for each trend, and the trends. Why specifically 3 axes where we see something a bit more, depending on the graph? Is there going to be performance fall off if we're from 10 to the 5th, 10 to the 6th versus 10 to the 4th? How's that look?
Yes, so the 3 axes are for the small, medium, and large models that I ran. I would have loved to provide more, but I ran out of time and didn't have enough computational power to really test 10 to the 7th, 10 to the 8th. In the machine learning literature, it is generally accepted that there's a linear log-log relationship for transformers when using validation loss on English. The reason I didn't try to show a log-log relationship here is that when your loss is 0, your log is very negative. So what I would hope is to continue to see in a log-log graph a downward linear trend. However, I would need further future research to test larger parameter counts to verify if that's the case. Of course. Thank you. I would like to do that I would like to test that as well. So DeepSeek has a thinking and a non-thinking model. Its non-thinking model performs roughly as well as GPT-4o does. There's always going to be some variability. Some of the models are better at coding, some are better at math. But on all the AIs that I tested that were not thinking, they all struggled with 4x5 digit and 5x5 digit multiplication. I would expect it having a very similar testing accuracy to GPT when it comes to integer arithmetic. Professor Brown.
So first, thanks very much. This is really interesting. It's great. So with sort of the models that ChatGPT and Gemini are all using, there's this rough idea that a smaller model with fewer parameters means less computing power. Right? But of course, they're all operating more or less the same architecture. So if with your model, say you have X parameters in your model, and we know that an X parameter version of your model will outperform an X parameter version of this other model, right? That's what you've shown, and that's what's cool. Is the energy required for an X parameter model
That's a great question, and I feel comfortable giving a computer science answer because I know that's what you would want. So, when we look at the information transfer, the dominating factor of energy in computation is this multi-head attention. It's O of n squared in terms of energy consumption and memory. And so, since the current transformer and the transformer both utilize multi-head attention, if you assume that they have the same number of parameters, it'll be roughly the same amount of energy. There's certainly some additional energy that is going to be taken by this LSTM, but it's linear rather than quadratic. And so as the parameter count increases, that becomes much less significant compared to the multi-head attention. And so there are more exact studies you can do to calculate the number of flops used. I've not run those studies, but I'm fairly certain that it would be almost exactly the same between a same parameter count, retrans versus transformer.
So roughly speaking then, when I look at one of your plots and you say that I get the same accuracy with my model with, say, half the number of parameters.
Correct.
Right, then we can also read that as I can get the same accuracy at half the energy required.
It would be a fourth because of O of n squared. So if...
Oh, okay, but no, I didn't pay attention to you. Thank you. I really just that.
Any other questions? Oh, we have one.
What has been the time here, Trident, you had a proposal?
Yes.
And we were very eclectic in your proposal. When you look back, did you achieve everything you wanted to achieve?
I did not achieve everything. I have a tendency to bite off more than I can chew, but looking back, I'm still happy, very happy with what I've achieved, and it has set me up to finish those things that I wanted to do in the future. And this is significant enough that it is publishable research, and I think it can make a very large impact on machine learning in the future.
You're very confident, yeah, about your next step. Does that mean that you go to grad school or something?
No, so I'm commissioning as a cyber warfare engineer, and there are cyber warfare engineers working on machine learning research. The NSA has got a lot of big computers, and I'm sure they'd be very interested in this. I love biting off more than I can chew.
Look back, honestly, look back romantically, the ChatGPT, whatever artificial intelligence programs, they just have this kind of idea, we can ask them anything and they can ask anything. If you can map how much that helps them to actually find what taught and what you don't. That's a part of the philosophical question, I believe.
Yeah, so it's certainly difficult, especially in machine learning, to train a model to utilize things that it has learned in an area that it has never been before. And so it would be very hard to prove new math theorems when it's not in the data set because it's new. My hope is that through using these types of architectures, it can hopefully learn the more underlying fundamental ideas of how addition works rather than memorizing a couple addition answers. And hopefully, sorry? That's the $1 million question, isn't it?
I'm on your $1 million kid.
Not yet. Hopefully sometime. But my view and is I think that using much smaller models and through mixture of experts, architectures, using variable computation, you can train specific layers that are very small to do very specific finite things. So rather than having one architecture that's trying to solve the entirety of arithmetic at the same time, let's say we had 10 architectures and we allowed them to interconnect and we allowed the model itself to choose how to interconnect and when to use it. We would hope that then it could specialize different of those 10 architectures. Maybe one would do addition. One would figure out multiplication. One would figure out subtraction. One would figure out order of operations. And then through piecing it together, it could learn those underlying truths and then use that to generalize to new problems. Currently, we don't have that. And what I plan on doing in the future with variable computation is trying to reach that. But again, I'm just a lonely undergrad with a dream. So.
Because I think that's the issue. I honestly think that's the issue. I need that underlying thing to work so much. But I don't know.
Any more questions?
I was just gonna ask real quick, I mean, kind of related to where you know going. Did you try, I imagine Robert tried, did you try training one model? Did you both tests? And see how member size and implementation affected?
I didn't because they use different vocabularies.
That was a bit about tokenization.
Yeah, so different tokenization. It would be interesting to see. I definitely think there would be crossover in terms of the parentheses using order of operations. However, I don't know how much crossover there would be from the plus, minus, multiplication versus and or negation. That would be an interesting test.
Let's thank our speaker one last time. For a few more minutes for the next one.
Thank you. Thank you.
major from Silicon, Washington. His service selection to medical corps, and he's a member of the Navy Defense Water Polo team. And in the fall, he'll be attending Harvard Med School.
Good afternoon, everyone. I'm Midshipman First Class Sean O'Boyle. I'm here to present my Trident research project titled Investigation of Host Protein Cleavage by Neuroinvasive Viruses. I know that's kind of wordy and maybe confusing right now, but hopefully we can break that down and we can understand what I did for this past year, but also previously during second class year. So spent a lot of time working towards this project, made a lot of progress, and I'm excited to share it with you guys. I also want to just shout out my research advisor, my academic advisor who served as advisors on my Trident project, Professor O'Carroll, Professor Jamer. Thank you so much for the support and the help. So yeah, let's get started. So the primary motivation, the most central concept that motivated me to take on this project is the growing threat of neuroinvasive viruses. Neuroinvasive viruses are viruses that can cause potentially deadly neurological disease. They pose a significant threat, and that threat is increasing every day as we see the spread of certain vectors like mosquitoes and ticks, but also as the climate changes and tropical environments expand where these viruses are endemic. 3 neuroinvasive viruses that we specifically have focused on this project are Zika virus, West Nile virus, and enterovirus 71. And these 3 viruses are increasingly widespread. And if you see this map, we see Zika virus is widespread in the Americas. It's increasingly widespread in Southeast Asia. West Nile virus is similarly prominent in the world, and this is growing every day. Not only are these areas large and they affect a lot of people, these are some areas of military significance. And developing ways to combat these threats is a significant aspect of force protection for our military and civilians. And so far, this is especially concerning because there's no FDA-approved vaccines for these viral threats, and work needs to be done to develop those sorts of treatments. Another significant aspect of the background to this project is the pathology, the disease encephalitis. Encephalitis is brain swelling. It can be deadly, and essentially what happens is there's this important tissue in our body made up of cells, and it lines the bloodstream, and it protects the central nervous system, the brain and the spinal cord, from inflammation. And when the blood-brain barrier breaks down, that can allow inflammatory molecules to leak into the tissue and result in a neuroinflammatory response, brain swelling, and potentially really debilitating disease and even death. Encephalitis is a scary thing, and I think it's one of the most scary things that these viruses can result in. And then another thing for our non-biologists in the room to understand that's significant to our research is DNA and proteins. So proteins are biological molecules that are made up of amino acids, and they serve diverse and important functions in organisms, especially in humans. And what codes for these proteins, what tells them to express in a certain way so that they have this function in the structure is DNA. And I think everyone's heard of DNA. It's like, the directions for how we express proteins. Viruses produce proteins. Viruses are basically a kind of like an organism that has a protein capsule and a genome, and it infects a host, and it replicates, and it makes more of those proteins required to replicate more. And humans also have proteins. These are significant to every function of our body. A little more about viruses and the way that these viruses are infectious is viral proteases. So the structure of these viruses, like I said, is this protein capsid that protects the genetic information inside of the virus. This is Zika and West Nile virus's structure. They share a similar structure, and enterovirus's structure is slightly different. But these viruses produce proteins called viral proteases. Proteins are proteases that their function is to target other proteins and cut them or cleave them. And this is really useful for the viruses because a really efficient way of producing the proteins that a virus needs to survive and replicate is to make one big long chain of amino acids, and then a viral protease can come and just cut that, and then all of a sudden you have like four important viral proteins from one long polyprotein. But when these viral proteases are in the presence of human proteins that potentially have the same sequence in the protein that originally the viral protease would attack in the viral polyprotein, if a human protein shares that sequence, there's the potential for an interaction between the viral protease and a human protein. And that's of concern. So the way we can predict these interactions between viruses and the proteins of the human body is through software. And specifically, Naval Research Laboratory has developed a machine learning software that looks at the cleavage site that viral proteases target in the viral polyproteins, and then it compares that to the human proteome. It looks at the sequences of human proteins, and it finds short stretches of homologous host protein sequences that are homologous to the target sequence of these viral proteases. These match up and allow us to predict if the Zika virus protease targets this specific sequence, and this sequence exists in a human protein, maybe the Zika virus viral protease will target this human protein. So looking at various neuroinvasive viruses, Naval Research Laboratory used this software to predict that 9 different neuroinvasive viruses, including Zika, West Nile, and enterovirus 71, they saw that they all target potentially the same human protein called ADGRA2. Now, ADGRA2, as a human protein, is important to the structure and function of this blood-brain barrier. If this human protein was targeted and degraded, and therefore the blood-brain barrier was no longer intact and functioning, that could be the cause of the breakdown that results in encephalitis. Encephalitis is a pathology that you see frequently when people are infected by these neuroinvasive viruses. So as we look to combat those, we want to look at how they actually function and what we can target there. And as a predicted target, the specific cleavage sites for ADGRA2, there are 3 marked by these amino acids, specific sites along the sequence on the ADGRA2. These are the predicted sites predicted by researchers at Naval Research Laboratory. And the hypothesis that guided this research is that we hypothesize that ADGRA2 is a target of Zika virus, West Nile virus, and enterovirus 71 viral proteases, as predicted by that software. But how do we test that? For one thing, we need to express and purify viral proteases from those neuroinvasive viruses. And then we also need to create an ex vivo model of ADGRA2 in a human cell so that we can test if in its environment ADGRA2 is targeted by these purified viral proteases. And that's highly complex, but I'm going to try to break it down really simply. First, we produce ADGRA2 in human cells that express this protein. Then we add viral proteases either to the outside of the cell or they originate in the inside of the cell, expressed alongside ADGRA2, and we see if those viral proteases target ADGRA2. And then we look at the protein fragments from the cell and we see if ADGRA2 was targeted and fragmented as a result of cleavage. And we use Western blot analysis to do that, which we'll get into. So, first thing, we need to express and purify these viral proteases from Zika, West Nile, and enterovirus 71. Another important piece of background for how we're going to do that is this idea that as researchers, we can have a target protein that is coded by a specific DNA sequence, and we can make it so that cells express that DNA sequence and produce that protein. The way we do that is we synthesize plasmid DNA. It's a circular stranded DNA. It has genes that code for protein expression, and we can insert a gene that expresses our protein of interest. And then what we do is we either put that plasmid in bacteria, we transform that bacteria, adding that portion of the genome, or we transfect mammalian cells with those synthesized plasmids, and then those cells can express those proteins, either AdGrat2 or viral protease, depending on what plasmid DNA we insert into those cells. So initially, we purchased three plasmid constructs that code for the viral proteases of enterovirus, West Nile virus, and Zika virus. We purchased these plasmids, and essentially the gene for the viral protease was under the control of a T7 promoter, meaning that we are able to induce the expression of this protein in bacterial cells. Essentially, we take this plasmid, transform bacterial cells with that DNA, and then we can induce the expression of that control gene by adding an expression-inducing reagent, in this case, IPTG. So taking those purchased plasmids, we grew the cells with the plasmids inside, and then we induced expression. And we saw very little difference in the expression of our target viral protease here at a little less than 37 kilodaltons. That's the mass of the protein. And we can see this gel. It sorts the protein products of the cells by the size of the protein. And we see that in all three situations, cells with all three different plasmids, there was not much difference between the uninduced and induced amount of our viral protease. Essentially, expression wasn't super successful. We would expect to see, very little expression of the protein and then a very, very concentrated expression of the protein, which we didn't see. And so we reevaluated our induction conditions. We increased the concentration of the reagent we used to induce expression. We changed the amount of time and temperature at which the cells were allowed to express the protein. And then we saw a significant change in the expression. But most significantly, we saw that the viral protease for West Nile virus, coming from the plasmid DNA 25, was the most concentrated. The expression seemed to be the most successful. So that was encouraging. It was a little discouraging that it wasn't as successful for the other two viral proteases. But with that successful expression, we moved forward with attempting to purify the West Nile virus viral protease. And in order to do that, you need to understand another concept, that we express this viral protease with a his tag. It's a repeated sequence of histidines, or the amino acid, and that allows this viral protease that's very complex to be targeted and detected so that we can visualize it, but also so that we can purify it. So we took the purified West Nile virus protease, or the expressed West Nile protease, and we put it in a nickel resin column. And the nickel binds really strongly to the his tag. And essentially, we can send those proteins from the cell through the column, and the column will grab the his tag and grab the viral protease connected to that his tag. And then we elute out that viral protease. And we were able to see that we had a lot of proteins initially, and then we performed this purification using the nickel resin column, and we had a very concentrated presence of the West Nile virus protease that we were trying to purify. But this West Nile virus protease that we purified had a his tag, and the West Nile virus protease produced by West Nile virus that potentially attacks AdGrat2 doesn't have that in the real world. So we needed to get rid of that his tag if we're going to have like an active viral protease for these investigations to determine if cleavage takes place. And essentially, the construct, the viral protease, has a certain specific sequence between the West Nile virus viral protease and the his tag. And we can target that sequence with the TEV protease. Essentially, the West Nile virus protease followed by the His tag. There's a specific cleavage site. We add the TEV protease. It cleaves at that cleavage site, and hopefully we get just the West Nile virus protease. And this, once again, is a protein gel that sorts out the fragments. And what we see is that we have dialysis so that we can actually add the TEV protease. We need to change the solution, the environment that the protein is in, so that the TEV protease can function. Then we add the protease, and we see that we go from very concentrated protein of a certain size, and now we have that same size but also smaller one and a very smaller one, which we hypothesize is that that's the West Nile virus protease and the His tag cut off. And then we send it through the column again, this time letting the West Nile virus protease go through and the His tag being captured by the column. And we see the purified West Nile virus protease. So at this point, we have successfully purified the West Nile virus protease, and hypothetically, it should be available for use in cleavage investigations. Additionally, although we haven't purified the Zika virus and enterovirus viral proteases, this process that we went through and trial and errored and figured out should hopefully be a blueprint for purifying the other viral proteases. The next step would be to create an ex vivo model of the AdGrad2 protein in a human cell. Basically, ex vivo meaning it's a living cell, it's a functioning cell, but it's outside of the organism. And we first need to get human cells that express AdGrad2. So this was actually the work I did for my capstone in the second semester of second class year. But essentially what we did was we worked to take a plasmid construct that had the gene for AdGrad2 protein under the control of a CMV promoter, which allows for the expression of the protein in a mammalian cell or human cell. And then we inserted a sequence right at the end of that protein so that we could visualize the protein once we use it in cleavage investigations. So we constructed this plasmid through a polymerase chain reaction that added that HA tag sequence after the AdGrad2 gene. We confirmed that this plasmid wasn't in fact the construct that we were hoping to get, and then we had successfully created a plasmid for the expression of AdGrad2 in a human protein. But we didn't want just to be able to express AdGrad2 in a human protein, we also wanted to be able to express the viral proteases in a human protein. And in order to do that, we took those purchased plasmids that allow for the expression of the viral protease gene in a bacterial cell, and we used PCR to amplify and then purify this gene for the viral proteases, and then insert that into a vector that allows for the expression of the gene in a mammalian cell. So that then we had plasmids for the expression of the viral proteases in mammalian cells. So first we had to actually get that viral protease gene. And initially it didn't work. We had to optimize the PCR, especially for the EV71 gene. But eventually we had these about 600 base pair fragments of the viral protease gene DNA. And then we were able to insert that into a linearized vector that allows for these proteins to be expressed in mammalian cells. We grew bacterial cells that had that plasmid, and then we purified it so we had a bunch of that plasmid. And then we sent that in for sequencing, and we saw that we had successfully confirmed the synthesis of 3 plasmids that each would allow for the viral protease expression in mammalian cells for Zika, West Nile, or enterovirus 71. The next step would be to actually grow the human cells. So the human cell line that we used was A549. It comes from lung cancer in a man, and we grew the cells in flask using growth media and in an incubator that allows the atmosphere to have CO2 for the cells to grow. Then we attempted to transfect those cells with the plasmid for the expression of AdGrad2 protein. This is images under the microscope of the healthy A549 cells that we then use for transfection. And then to transfect, we take the plasmid DNA that expresses ADGRA2 in a mammalian cell. We combine it with a reagent called lipofectamine that forms a lipid vesicle around the plasmid DNA. Essentially, we have a little lipid vesicle with the plasmid DNA, and that allows the plasmid DNA to go into a cell where it can be expressed, and we can express our protein that we want in the human cell. Then to confirm if that happened, we use Western blot. We lyse the cells, we get all the debris, all the proteins in the cell, then we separate it out by fragment size, right? See the size of the protein so we know what protein it is. Then we transfer it to a membrane and treat it with antibodies that allow us to visualize that using a near IR imager. And what we found was we successfully added the antibodies, and we had to control the protein actin, which is present in almost all cells, and that was successfully expressed. But we didn't see any evidence of ADGRA2, which is about 14,000 Daltons or 14 kilodaltons. We didn't see evidence. So that was an unsuccessful transfection. But we did successfully grow healthy A549 cells to continue this research. And we do have a plasmid for the expression of ADGRA2. We just have to perfect the transfection. The future work that can be done with this is taking the human cells with the ADGRA2 and adding viral proteases to the outside, which would be an exogenous cleavage analysis to see if the ADGRA2 is cleaved. Or now that we have the ability to express viral proteases inside the cell and ADGRA2 inside the cell, we can co-transfect a human cell for the expression of all of those proteins and then see if the proteases originating inside of the cell cleave ADGRA2 and result in fragmentation as predicted. Some acknowledgements. I'd like to thank my research advisors, the Trident Scholar Program, especially Professor Schroeder, Dr. Patricia Legler from NRL, who was the impetus for this project, that we were a small part of a very large project. That is no longer working out. And then some fellow midshipmen who I worked with in the lab and who are going to be carrying on this project. And I'm ready for any questions. Thank you for your time. Yes.
What are your plans after graduation, and do you plan to continue research after graduation as well?
Yeah, so after graduation, I'm going to medical school. This project is really contained here, so I don't know if I'll be able to continue to do the experimental work, but I think a lot of the work that we've done in working towards testing the hypothesis and doing the cleavage investigations, I can have an active role in helping to carry that on and providing my insight and mentoring third class Solomon Desta and doing that, which I think will be satisfying. It's not exactly like the type of research I think I'll be engaged in medical school, but it is really awesome to see the basic science, the biomedical sciences that contribute to, diseases that cause suffering that hopefully, I'll learn to alleviate. And I think that's really satisfying. So it really put me on that trajectory to want to do that. Yeah. Yes, Professor. Or Professor Smith, yeah.
So what's known about ADGRA2? I mean, in terms of its actual role, and is it found in other mammals?
Yeah. So specifically, I don't know if ADGRA2 is found in other mammals, but looking at ADGRA2 in Homo sapiens, which is what I've researched, it's present actually in a lot of places in the body. It's a G protein coupled receptor, so it's important for cell signaling. And specifically in the body, it is in endothelial cells, and I'll go back to ADGRA2. It's specifically in endothelial cells, and it is found in the endothelial cells in the brain. And essentially, it's known to be a mediator in the flow of certain inflammatory molecules or stopping inflammatory molecules from crossing over an endothelial membrane and going into the tissue. So it is a G protein coupled receptor, and that's its function.
For the AI method that identified the ADGRA2 as or was it like the structure? Like, I guess how big is the sequence that it's recognizing?
So it's not a very long sequence, and it is based off the sequence.
Okay.
It uses like just the sequence, the proteome of the body, the data, and compares it. But that's kind of like vague, and so how can we predict that would happen? Well, before Dr. Legler left NRL, and we were just doing this project on our own, we were just going to be doing the cell culture stuff and the cleavage studies, while they at the same time were doing in vitro studies of just the cleavage sites with the viral proteases. And what they had found already was that this prediction about Japanese encephalitis virus, they predicted that it cleaved AGRAT2, and in an in vitro cleavage study, they found that it cleaved AGRAT2. And so a lot of this project is, like learning more about AGRAT2 and that the role in encephalitis and the diseases caused by these neuroinvasive viruses. But at the same time, by doing this research, we're basically testing, does this software give us good predictions? So we have seen that it has given good predictions, and we want to continue to confirm that. And that's part of what we're doing.
Thank you.
Yes, Professor.
So if you're able to confirm that that is like a cleavage site that's targeted by the proteases, like where do you go from there to say like how to protect yourself against these viruses or infections?
Yeah, I don't exactly know. I know that understanding the interactions between a virus and the host protein is important. I think it's a big step to even know that it's AGRAT2 or that it's a protein of the blood-brain barrier. But I think various drugs can be developed to protect AGRAT2, to inhibit the function of the viral protease. That will be a potential use for it. But this is like the first step of like a 10-step process that causes a lot of money and a lot of time to develop treatments and vaccines just with this like basic research. So I think developing drug targets and maybe even treatments, to stop the infection, but also to stop the pathogenesis once someone is infected by the virus. It's kind of vague, but I think I'll learn more about that soon. Yes, Professor.
Thank you for a great talk. I'm curious about the generalizability of cleavage sites and proteases. Is it generally true that it is on the outside of proteins where there are more hydrophilic sequences, because those are just simply more accessible to the proteins? Or are there no patterns that you can really discern from looking across different proteases? And in particular, even the ones that come from these kinds of viruses?
Yeah, so I think part of the reason why we're doing endogenous and exogenous, we have 3 predicted cleavage sites, and I think all these are feasible, but we don't know which cleavage site exactly, and that's why these investigations might be useful. So far, it is just based off of the amino acid sequence, but I think what we were trying to do with generating the 3D model of AGRAT2 was to see, on a G protein coupled receptor, we know that the 7 transmembrane barrels, are in the membrane and the rest is inside the cell. And so we can start to understand, what is actually sterically available for viral protease. But I think more of that information can come from these investigations. Yeah.
Any questions?
Yes.
Were there any, do this work safely? Were there any safety concerns in doing this type of research? Why there might not be safety concerns?
Yeah, so actually, we originally, when looking at projects of interest, Professor O'Carroll has a virology background and interested in looking at viruses and interactions. We were interested in looking at the Crimean Congo hemorrhagic fever virus. But we found out that there isn't any way to analyze that virus itself without it not being at a biosafety level that our institution is able to handle. Long story short, all of the work that we're doing here is biosafety level 1, which is safe. Obviously, we're using reagents that could, hurt our skin if ingested or in our eyes, but you wear goggles and you wear gloves, and for the most part, these things are basically inert, just the protease, not with the protein capsid that allows the virus to actually infect people. It doesn't have all the means of infection when it's just the protein. So it's safe, it's good, I'm good.
Also, a follow-up I would relate, in the early parts you discussed, having to change a number of factors to see the expression you were looking for. And that raises the question that there's a phase space of all the various conditions and variables, right? And so, you know, to take this research to the next level, is that an important factor, like being able to explore that phase space?
Yeah, this one part of this project was kind of nestled in a much larger context of a much larger research project that was going to be going on at the Naval Research Laboratory before it got canceled. You could do a whole project looking on optimizing the expression of these one viral protease in this cell and the conditions of how to do that. But when we had to change, we saw poor expression, what we really just did was a literature review and look at some other experiments that are published where people were expressing viral proteases in bacterial cells. And we just played around with those, the concentration, the temperature, the time of expression. But there is a lot more research that would need to be done to corroborate these findings, like I said, in vitro clinical studies and other things.
When he says we, he means him. He did all the literature review and all the work should be done to, and he spent a lot of time doing things that he's not showing because he was troubleshooting.
Hey, looks like our speaker will have come to our last speaker for these Trident Scholar presentations. Thank you for all of you for joining us and listening to their talks. And hear next from Jillian Onke. She's from the 18th Company Chemistry Region. She's from Wayzata, Minnesota. Her service selection was Medical Corps. And she was a 3-year member of the Navy Women's varsity rowing team, and this past year she was goalie for the Navy women's hockey team. Yeah. She will be attending medical school in the fall at USIS in Bethesda, Uniform Services University of the Health Sciences.
Jill?
Good afternoon, everyone. My name is Jillian Onke, and today I'll be talking about my project titled The Evaluation of Bio-Based Polyesters and Additive Manufacturing, working with Professor Pinto in chemistry and Commander Slager in mechanical and nuclear engineering. First, to start off, what I'll be talking about in this presentation, I'll start off with the DoD application, and then I'll go through the background of my project, the chemistry, then the engineering side, and then I'll walk through what my time in lab actually looks like and conclude with future work that I propose. First, to start off, the DoD application. The military prides itself in having mission-ready, medically qualified personnel. However, a career in the military can often result in a physically strenuous lifestyle, resulting in physical health implications later on. One of them being osteoarthritis, which is characterized by the breakdown of cartilage at the ends of bones, causing the bones to rub together, creating friction and pain. The problem with osteoarthritis is that there's no permanent solution for this disease, and so what I propose is building a biocompatible polymer that can act as a scaffold. Right now, doctors are inserting chondrocytes, which are cartilage-producing cells, into these sites. However, there's no structural support for those cells to latch onto. By creating a biocompatible scaffold, that can be that structural support to create and promote the growth of cartilage. For my statement of work, I've grouped my project into 3 main objectives, the first being the production and purification of the polymer, the second, characterizing this polymer based on its structure, physical, and thermal properties, and then lastly is testing the ability to use the polymer as a material in additive manufacturing or 3D printing. So first, let's start off with the most basic idea of this project is that we are producing a polymer. A polymer is a macromolecule comprised of subunits called monomers. These monomers are linked together to create a polymer. More specifically, we are producing a copolymer. So there are 2 distinct monomers that are linked together to create a copolymer in either an alternating block, or in this case, we're creating a random pattern copolymer. What is novel about our polymer is that it has an azide functional group, which is represented by this little red dot. The azide functional group allows for the polymer to undergo a secondary reaction in order to create a modified copolymer. This reaction is called click chemistry, and it's fast, efficient, and has little to no side products. Our polymer can also be categorized as a polyhydroxyalkanoate, or PHA for short. PHAs are bio-based polyesters that have been seen in multiple FDA-approved biomedical devices, such as sutures, stents, and pins. The way that we categorize PHAs are based on the length of their carbon chains. So we have short chain lengths, which are 3 to 5 carbons, and then medium chain lengths, which are 6 to 14. The length of the carbon chain determines the physical property. So shorter chain lengths tend to be more brittle, whereas longer chain lengths tend to be more elastic. So just like when you're baking a cake, the ratio of your ingredients determines the quality of your product, the same for our PHAs. The ratio of our ingredients, the monomers, will determine the physical properties of our polymer. However, there are 2 disadvantages to PHAs. The first is that there's poor control over the monomer composition. This means the actual ratio of our monomers. The second is that they're unreactive. So once they've been made, they're stagnant and they cannot be changed. Our solutions to these problems are first using an engineered E. coli strain. So by using a plasmid, we can know that the molar ratio of the polymers, of the monomers that we add, will be resultant and seen as the ratio in the product of our polymer. The second is introducing reactive side chains. This is where the azides and click chemistry come into play. So this is the reaction. We have our 2 monomers. We have a short chain length, and then we have our medium chain length with the azide, the N3 present, which link together to create our PHA copolymer. This is an example of what the click chemistry reaction will look like. We have our polymer, the 2 monomers, and the azide can react with the cycloalkyne to click together to create our modified copolymer. The R group can represent any functional group and it can be geared towards what you desire in the final product. So if you're looking to make it more brittle, it could be a shorter chain length, or if you're looking to make it more viscous, it could be adding a different functional group such as a hydrogel. And then this is the product that we intend to make. So we have our short chain length, which is the butyrate, 4 carbons, then azeto is the azide, and then octanoate is our 8 carbon chain length. And for short, I call it PHBO N3. Now switching gears to the engineering side of my project is additive manufacturing, which is a layer-by-layer method of creating a product. This product can be made from liquid, solid, or powder material. In my project, we use a solid filament. Additive manufacturing has really taken off in the past few years because of its ability to customize products. Especially for the medical field, we can customize a product to be geared towards a specific patient. Additive manufacturing has also been seen in other industries, such as biotechnology and computer software. The specific type of additive manufacturing that we use in this project is called fused deposition modeling, or FDM. In this method, we use a thin plastic filament to print. But first we need to make that filament. And what this process looks like is we have our extruder, and in the form of pellets, the pellets will enter into this hopper, funnel down into a heated chamber, and then be pushed through the chamber by this revolving screw. The filament then exits the nozzle and then is wound around a spool, in which the spool can then be fed into a hot nozzle to be 3D printed, where it's important that the original layer that goes down will solidify and coalesce before the next layer is added on top. Now I'll walk through what I actually do in lab, starting off with the research objectives. So first is to purify and produce the polymer. So we first start off with our fatty acid feedstocks. These are the monomers, in which we can then add to our transformed E. coli bacteria and to create this final product. What this looks like is we have our petri dish with our cells that have been transformed with the plasmid. We add one colony and inoculate a shake flask that has Lennox broth, kanamycin, and then our fatty acids, which are the monomers. And they'll shake and be heated at 30 degrees Celsius for 48 hours. From there, we can condense the cells and dry them. And the way that we pull the polymer out of the cells is by using this apparatus called a sock slit, in which chloroform is continuously evaporated and then recondensed over a 5-hour period. When it is recondensed, the chloroform pulls the polymer out of the cells, so then at the end, in the round bottom flask, we're left with chloroform and our polymer that is dissolved in the chloroform. We can then evaporate the chloroform away, and we're left with the residue. When you add this residue to cold methanol, it will resuspend and pop out into solution to look like this white fluffy solid, which is our product. This data is analogous to our percent yield, and so 23% is the percent of mass of the polymer that we're able to attain compared to the mass of the dried cells, which is CDW, cell dried weight, and then our percent mass. And then in this experiment, we are aiming for a 90% of our short chain length to a 10% of our medium chain length, and are averaging about 86% of the short chain length. And then we also, as a control, produce the polymer without the azide. So that's just PHBO. Next, our next objective is to characterize this polymer. So we have 5 different instruments that we used to characterize its thermal, physical, and structure properties. And basically all of this data was used to predict how the polymer will behave when it is heated and extruded in additive manufacturing. So first is infrared spectroscopy. This was used to confirm the presence of the azide in the polymer based on this peak right here at 2095 inverse centimeters. Next is nuclear magnetic resonance spectroscopy. So based on the integration of the peaks, we can determine the ratio of the 2 monomers. So this is PHBO, and with this integration of this peak representing the hydrogens on the 8th carbon, we can determine that it was 76% butyrate and 24% octanoate. And then for our PHBO N3, we use the field that's more downfield because it's in a more polar environment to integrate the peaks to learn that it was averaging at about 86% butyrate and 14% of the octanoate. Next is gel permeation chromatography. This was used to learn about the polydispersity of the polymer. So what this means is this MW to MN ratio, ideally, in a perfect scenario, it's 1, meaning that each strand of the polymer produced is the same length and size. However, because our polymer is produced by a cell, that is not the case. It is in an uncontrolled environment, so that's why this ratio is slightly elevated. Next is thermal gravimetric analysis. So in this, the sample is heated up, and when we see a sharp decrease in weight, that is when the polymer degrades. So at the point of inflection, we can determine the temperature at which the polymer degrades. So we know that we cannot exceed 237 degrees Celsius without the polymer degrading. So that is our ceiling in terms of temperature. Next is differential scanning calorimetry. And so the polymer, the sample, is heated and cooled in 2 cycles. And based on the data, we can look at these 3 peaks to learn about the glass transition temperature, the temperature at which the polymer crystallizes, and then lastly, the temperature that the polymer melts. So we know when we're printing, we have to exceed 130 degrees Celsius in order to melt and extrude the polymer. My last objective is to test the ability of the polymer to be used as a material in 3D printing. What this looks like is first creating the filament using an extruder. We did this process 2 times, first to learn how the method works with commercial PLA. So we took the pellets, we added them to the hopper, they go down, funnel into the chamber, then exit out of this nozzle in which they flow over this air path, which forces convection onto the filament to cool it, before it enters through these 2 wheels to gauge the diameter of the filament, and then is wound around this spool. What is the most important parameter of this process and the filament that's produced is the diameter. Because the printers are very sensitive, it needs to be 1.75 plus or minus 0.05 millimeters in diameter. Then the second time we produced filament, we doped PLA with our polymer without the azide. So PLA with PHPO, and we just mixed it in and then added it to the hopper to create the filament. This is an area of research that we're looking to keep exploring in the future, because right now we just have the mechanically blended, but then I'll also speak about what chemically blending looks like at the end. And so after we've printed, we've created the filament, the next step is to create dog bone samples in order to test for tensile strength. So this is the raster pattern. So this is what the computer software looks like before we were printing. And then with the printer, we're able to print the dog bones using a Prusa printer. So this printer is less sensitive than other printers that are used in 3D printing. So we can manually insert the filament into the nozzle to create the dog bone sample, which looks like this. Next, we perform tensile strength tests on the dog bone. So we can see clamps attached to the top and bottom of the sample, and then the green device is an extensometer, and it measures the position and how much stress the polymer is stretching. And so we can create a stress strain curve. And the first part of this graph is the elastic region. And so we can learn about Young's modulus, which describes the stiffness of the material. So a steeper slope correlates to a more stiff polymer. And then our max point is the ultimate tensile strength. And so that is the max stress the polymer can withstand before it starts necking, so it starts stretching apart before it breaks at failure. And what was interesting about this is we had 2 different sets of dog bones. So we had dog bones that were filament that was pure PLA, polylactic acid, and then our PLA that was doped with our polymer. And we can see that ultimate tensile strength and the Young's modulus both increased in our doped dog bones. And so even though it was doped with such a small % of our polymer, we can still see that it can withstand more stress and is also a more stiff material when it has been doped. Lastly, to talk about future work, one of the limitations we had this year was the scale and the volume of the polymer produced, because each cycle of polymer production takes about a week to do and averages about 330 milligrams per cycle. So it really limits how much we can print at one time. And so a bioreactor optimizes the environment that cells grow in to include temperature and pH. And so instead of producing a couple hundred milligrams per week, it's going to be multiple grams. And then next would be exploring chemical blending. And so right now I have chemically blended PLA with our azide polymer by dissolving it in chloroform and then resuspending it in methanol. However, the next step would be to pelletize it to create these uniform pellets to be able to extrude and print with it. And then the next step for future work would be looking at performing click chemistry reactions. So to actually prove that the azide and the polymer has been blended in the PLA, we can react it with a fluorescent tag to check for the presence of the azide. And then lastly is to test other monomer ratios. So right now we're aiming for a 90 to 10% monomer ratio, but that can be easily changed to explore the physical and thermal properties of that polymer. And lastly, I just want to conclude by re-emphasizing the goal of this project was to create a copolymer that is biocompatible and can serve as a material for 3D printing in the hopes that we can print a scaffold that can be used as a structural support for patients with osteoarthritis. I want to thank the people that funded this project, to include the Office of the Undersecretary of Defense for Research and Engineering, the Office of Naval Research, the chemistry department here, as well as the Trident program, and lastly, working with Professor Pinto. Any questions?
That's very nice. I'm curious about, so you did the tensile strength testing.
Yes.
What do you know about the biological materials this is intended to replace? What are their tensile strength problems?
So I don't have data for that, but the problem with current material that's being used in a biomedical setting is that when it degrades, it creates inflammation and makes the, like where it's implanted in the body, acidic. And so that's the beauty of our PHAs, that when it decomposes, it's not going to be harmful to the environment because it's just carbons and oxygen. It's not going to create additional inflammation in those patients. Professor Basta?
Did you find at all that the concentration of the fatty acids you were adding to the media that the bacteria were growing in, was there like a sweet spot in terms of concentration? I'm just wondering if those would be sort of like acting almost as a detergent to E. coli at all as you were growing.
So right now, the calibration curve is being created to determine the ratio of the monomers, the fatty acids, versus how they actually are in the monomer, or in the polymer when it's produced. But right now, because we're so close to like actually what we're intending to do, like we're at 86% and we're intending for 90%, we haven't really looked into seeing that as a problem for polymer production. That makes it a good question.
Yes, and then my second question is, do you know how these polymers are being generated in cells? Like, are they enzymatically generated?
Yes, there's a biosynthetic pathway that's targeted with the plasmid.
Okay, thank you.
Yes. Professor Sweet?
Yeah, kind of related to that, I was wondering if you had to do any troubleshooting or make any adjustments to the bacterial growth to compensate for the fact that A, you're putting in a non-native substrate for this enzyme pathway, presumably, and B, the reactivity to the azide. Did you have to lower the temperature of the bacteria, things like that?
In terms, so when we created in the polymer production process, it doesn't change regardless if we're using the azide or not. What was the first part?
I was more wondering about in the bacteria, does the azide cause a problem, and did you have to do anything to compensate for that?
No, the azide has not caused any problems. In terms of quantity of polymer produced, it's very similar from the azide to the non-azide. Yes, Professor Ham.
Thank you for the nice talk. I have a question about the actual printing. Once you are ready to you have your film made or print it, is the resolution of an FTM type printing setup such that you could make a scaffold that's appropriately sized? Because I'm sort of thinking like if you want to have cells that can go cartilage, you'll probably want a sort of like matrix type of setup. Can you comment a little bit about that?
Yes. So right now, the printers we're using are bamboo printers. They are a higher quality. It's kind of like a medium level quality right now. We started looking at MakerBot printers and then just to learn about 3D printing, and then right now we're looking at bamboo printers. But I know that the engineering department recently acquired a printer that's biomedically certified to print and be sterile. And so I think once we have really cemented the filament process, because right now the problem is creating a filament that isn't variable in diameter, because the Philobot extruder is very sensitive, so even the slightest increase in speed of the screw or how fast it's spooled can impact the diameter. And so I think once we create a filament that is very uniform in diameter, we can excel to a higher quality printer. Dr. Fitter?
Can you explain, what was the rationalization for the azide cycloaddition reaction, specifically with cyclooctane?
So the azide is what separates our PHA from other PHAs. And so our polymer can undergo a secondary reaction. So if we're looking to make the polymer more viscous and be more compatible to the human body, I've looked at attaching a hydrogel to the polymer to make it more fluid, and then the idea is to inject these chondrocytes, cartilage-producing cells, into this more fluid matrix. Versus other PHAs are stagnant and cannot be changed.
Thank you.
Okay.
Thank you for your talk. So you mentioned a 23% yield. So compared to other bacterial processes where you're giving them these non-natural feedstocks, how does that compare? It doesn't sound, I mean, it's not impressive as a yield, but it might actually be quite good.
So that 23% is normalized to the weight of the cells after they've been incubating and dried, and then also so it's the mass of the cells compared to the mass of the dried weight per the liter of broth that is added. And so it's analogous to a percent yield, but it's not the exact same because it's versus the mass of the cell.
And how does it compare to other processes like this where you've given cells non-natural reactants to make into polymer?
The only cycles I've done are with the azide, the PHBO, and 3, and then just PHBO. So they're similar in terms of like 23% and about like 30%.
And in the literature, are there some examples where that's been done by other research groups?
There's been, in terms of the polymers that's been made, the other polymers have been with different monomers. And so we're the first group to be using the butyrate and the octanoate. So there's nothing.
And with those different monomers, are they getting 23% or are they getting more? Are they getting less?
They're about the same.